Hello and welcome back to High Peak Education. I would like to perform a calculation of rotational dynamics using torque and also rotational kinematics. This is somewhat of a more fun problem, but it's also somewhat long. So we have Zod. This is General Zod, who's the arch enemy of Superman. By the way, this is General Zod and Superman from the classic movies from the late 1970s and early 1980s. So Zod decides to slow the rotation of the Earth to once per 28.0 hours by applying an opposing force parallel to the equator. Zod can exert a force of 4.00 times 10 to the 7th newtons. That's about 9 million pounds. Superman does not seem concerned, however. How long must Zod push with this force to achieve his goal? Well, let's go ahead and write down what we do know. So here's General Zod and decides to slow the rotation of the Earth. So why don't we first start by sketching the Earth? So here I have an approximate rough sketch of the Earth. Let's go ahead and model the Earth as a solid sphere. And when I say model the Earth as a solid sphere, we know that the Earth probably has liquid rock on the inside, but we don't know exactly what's in the interior of the Earth. Furthermore, we also know that the Earth, even though it's very close to a perfect sphere, it actually has a somewhat larger equatorial radius than it does polar radius. Because we believe the Earth is somewhat liquefied on the inside, it's slightly depressed at the poles. So in reality, Earth is an oblate spheroid, but I think for simplicity, let's just model the Earth as a sphere because it's very, very close to a sphere. So here's General Zod, and he's going to push with a force that is parallel to the equator. So let's go ahead and sketch that. Now, I think that if you also consider, before we go to that point, that the Earth rotates. So let's let this be the Earth's axis of rotation. So here's Earth's axis of rotation. I think the Earth rotates this way. Okay? So let this be Earth's axis of rotation. I think the Earth rotates this way. In other words, it rotates counterclockwise when viewed from above the North Pole. Now with that in mind, what about General Zod? Well, Zod has this force, and it's also parallel to the equator. So if he's trying to slow the rotation of the Earth, that's rotating counterclockwise when viewed from above, I think General Zod's force is something like so. This is just a sketch. So let's call that Fz for General Zod. Okay? So that's the force that General Zod's pushing with. But notice that. Let's also assume that it's exactly perpendicular to the radius of the Earth. Okay? So let's let this be the radius of the Earth. Some point from the center out to the point where General Zod is pushing. Okay, let's also write down our other knowns. We know that the time it takes for the Earth to make one revolution is how long? Well, that's 24 hours. So you could say the initial time is 24 hours, and then the final time that General Zod's going for is 28 hours. Now, by the way, let's assume both of these have 3 significant digits, and we might need to convert those in as we go along, but let's keep going. So we know Zod's force. Superman does not seem concerned, however. How long must General Zod push for this force to achieve his goal? Now, this is the initial time for a single rotation. So this is the initial time for a single rotation or revolution. And that's the same with this time. So these aren't really sort of times in terms of kinematics. They're really times in terms of angular velocities. Now in terms of one single rotation, what's the angular displacement of one single rotation in radians? Well, that's going to be 2 pi. So I think we can calculate the initial angular velocity of Earth and the final angular velocity of Earth. So omega initial and omega final should be 2 pi radians over 24 hours and 2 pi radians over 28 hours. So we need to get hours, that 24 hours, into seconds, because radians per second is going to be the primary unit we'll work in. So let's go hours. Let's go hours on top. 1 hour, there's 3,600 seconds. For every 1 hour, there's 3,600 seconds. Hopefully you know that conversion. For every 1 hour, there's 60 minutes. For every 1 minute, there's 60 seconds. So there's 3,600 seconds per 1 hour. So we should take 2 pi divided by 24 and then 3,600, and then 2 pi divided by 28, then 3,600. So let's get this omega initial and omega final, because I think we'll need those. Let's do a fraction stack. Let's do alpha F1, numerator over denominator. Let's do 2 times pi divided by 24, and then also divided by 3,600. So let's write this down. 7.27 times 10 to the minus fifth, and that's units of radians per second. Now, by the way, this initial angular velocity of the Earth is a very well-known angular velocity. That's sometimes just called capital omega. And this capital omega is a very well-known number. You could look this up in astronomy books, other geophysical books. It's the angular velocity of the Earth. And by the way, this is calculated very precisely whenever very precise calculations are need to be performed. But we've got it at least to 3 significant. Let's perform the same calculation, except now let's do for every 28 hours. So we just have to change that to 28. So we've got 6.23 times 10 to the minus fifth. So 6.23 times 10 to the minus fifth radians per second. Okay. Now, what we're going to do is we want to think about, okay, is this force of Zod related to something else? Well, yes, it is. It's actually related to torque. So since Zod is pushing with a force at a radius that's perpendicular to Earth, it's related to a torque that's on Earth. So because the force I sketched in red, let me go ahead and also use red for the torque here. So the torque from General Zod should be the force from General Zod times the radius, and that's the radius of the Earth. That's the radius that General Zod exerts the force at. Notice we don't need sine of phi here, because I think that phi is exactly equal to 90 degrees. And we know the sine of 90 degrees to be exactly 1. So this force and this radius are exactly perpendicular to one another. Now, that torque is also related to another kinematics variable, angular acceleration. Because what we're really after in this problem is the time that elapses. So that's a kinematics variable. But we want to know maybe the angular acceleration, perhaps, that's what tau seems to suggest, to get us another kinematics variable for rotation to solve this problem. Now, let's remember also how torque is related to angular acceleration. So torque, you recall, is equal to rotational inertia times angular acceleration. Well, what is the rotational inertia? We said we're going to model the Earth as a solid sphere. So this rotational inertia is the actual Earth. So that's the rotational inertia of a solid sphere. And I think we know what the rotational inertia of a solid sphere is. That's going to be 2/5 times mr squared. Now, by the way, let's put a subscript e on here for Earth. Okay? So 2/5 m of the Earth, radius of the Earth, squared. So let's go ahead and substitute that in, substitute this expression in for torque, and then solve for alpha. So we've got the force of General Zod times the radius of the Earth is equal to 2/5 mass of the Earth times the radius of the Earth squared, it times alpha. So if we want to solve for alpha, I think we need to divide by mass of the Earth, and then one of these radii of the Earth will actually cancel. And then we can also multiply by 5/2. So I think we've got 5 times the force of General Zod over 2 times the mass of the Earth times the radius of the Earth. Okay. So this is going to be the alpha. So we probably need that in these kinematics. So let's calculate this first. Okay, so 5 times the force of General Zod. We said that that was 4 times 10 to the 7th newtons. 4.00 times 10 to the 7th newtons. And we divide that by 2 times, what's the mass of the Earth? You can look this up. It's approximately 5.98 times 10 to the 24th kilograms. You can look that up in many books and online sources. The fact that I know that memorized makes me a big nerd. And then the radius of the Earth. Now, by the way, I'm talking the average radius of the Earth. This is the equatorial radius, which is a little bit larger. But the average radius of the Earth is about 6.371 times 10 to the 6th meters. Okay? That's approximate. Most people know that at about, 6,370 kilometers. So you can convert that to meters. All right. So let's go ahead and perform this calculation. So let's get a fraction stack. Alpha F1, numerator over denominator. So we've got 5 times 4 times 10 to the 7th over 2 times 5.98 times 10 to the 24th times 6.371 times 10 to the 6th. Okay, so let's write this down. So alpha ends up approximately being 2.62 times 10 to the minus 24th radians per second squared. 2.62 times 10 to the minus 24th radians per second squared. Now notice this is a pretty small angular acceleration. That's because the Earth is extremely massive, has a huge rotational inertia. But General Zod pushes with a very large force, but still doesn't seem to be slowing the Earth all that much. And General Zod wants to change the rotation rate of the Earth by several hours per revolution. So let's see how long this would take him. Now, by the way, notice that we have 1, 2, 3 kinematic variables. We're looking for this fourth one, and the choice of which kinematic equation to use depends upon the ignored variable. So I think we'll ignore the angular displacement. So I'm going to copy these important variables and go on to the next board. So I will see you in just a moment. Okay, so now that we're on the next board, let's say we're going to ignore the angular displacement. So that's going to tell us which kinematic variable equation we should use. Remember, this is rotational kinematics for constant angular acceleration. So I think we should use the definition of acceleration equation. That's omega final is equal to omega initial plus alpha times t. And by the way, this t is the delta t. All right, so we can solve this for delta t by saying omega final minus omega initial by subtraction. We're using algebra to solve, dividing by alpha is equal to delta t. And we can put all the numbers in. So let's do that. Delta t is omega final, which was that 6.23 times 10 to the minus 5th radians per second minus 7.27 times 10 to the minus 5th radians per second, and divide that all by the alpha, the angular acceleration of 2.62 times 10 to the minus 24th radians per second squared. So let's calculate this. So alpha F1 fraction stack 6.23 second EE, that's times 10 to the minus 5th times, or sorry, not times, minus 7.27 times 10 to the minus 5th radians per second, and divide that by 2.62 times 10 to the minus 24. Okay, so the calculation gives us, now by the way, the final angular velocity is less than the initial angular velocity. So given that we got a negative number here, the reason for that error, if you will, is that the alpha was actually a negative. So General Zod is slowing the Earth down. So we should have made this a negative for the alpha, this a negative. Back to the earlier board, we should have had this torque was clockwise. So given that this torque was clockwise, we should have written a negative here, and then we should have written a negative here, and then also a negative here, and a negative here, and a negative. Okay, so it should have been a negative alpha the whole way through. So we'll just read that time off as if it's positive. 3.96 times 10 to the 18th. 3.96 times 10 to the 18th, and that's seconds. Now, this may not seem so obvious to you how large this is, but let's go ahead and see how many hours there are in this. So let's keep this number on our calculator and let's divide by 3,600 seconds. Now, by the way, I'm just going to divide by negative 3,600 just to get rid of that minus sign. So that's 1.1 times 10 to the 15th hours. And then if we divide that by how many hours are in a day? Well, 24 hours in a day. So there we are. And then how about we divide that by how many days in a year? 365. So we get 1.26 times 10 to the 11th. 1.26 times 10 to the 11th years. That's extremely long time. Notice that indeed that would be a significant change to the Earth's rate of rotation, but it turns out that General Zod does not push with a significant enough force to really change the Earth's rotation rate instantaneously. It turns out that, I mean, even if it takes several hours for Superman to thwart him, Superman with his great feats of strength can restore the Earth to its regular rotation rate. Alright, so we're all so happy that Superman is here to help us. He stands for truth, justice, and the American way, and also for lots of great physics videos. So, thank you very much for your attention, and thank you for watching High Peak Education. Please smash that like button, and please share this content with those that you know. And please subscribe to the channel. I look forward to seeing you in the next video. Thank you for watching.